we are nearing the end of chapter 17, right? Is that what it is?
Yes.
Yeah. And we've got basically just one more topic here to go through, which we'll definitely get through today. And we'll take a look at a couple of typical problems that we might end up seeing from that section. And then we'll spend a little bit of time on Friday there, just kind of going through some of the other odds and pieces and bits and ends from that comes out of this chapter here. And then we'll keep moving on, right? The next chapter is, I believe it's on the free energy is what it is. So we'll kind of switch gears a little bit to go start to answer the question about why do some reactions happen. Basically, why does, I guess, the simple question is why does water evaporate at room temperature, right? But a little bit more complex than that, but don't worry, we'll kind of elaborate on that a bit. But we'll change gears away from equilibrium is all I'm really trying to tell you guys. So I can tell two of you guys are excited about that. So we've done enough of this stuff, and we get it. All right. So we'll do more horrible math, though, so that'll be good too. But anyway, but yeah, I'll chat with you guys about that on Friday. All right, so I think that's kind of all I just needed to mention with you. Yeah, what's that?
Will we have a quiz on chapter 17?
Yeah, I'll put that up sometime next week or something
Okay.
like that. Yeah. Like I said, I try not to give you guys a quiz on the exam week unless there's a really good reason for it. What's up?
Will the exam today be happening in the labs?
Yeah, they'll be in the labs. I couldn't find the rooms for today. Tuesdays are a little bit easier just because that's when most everyone has labs. It's like a little bit more free time, but Wednesdays are not. So, yeah, unfortunately, yeah, we'll be in the same uncomfortable chairs, but it's all good. Okay, cool. So we'll get started. We'll get started with prayer, and then we'll continue on here. But Lord, we thank you for another day and another opportunity, Lord. And Lord, with the millions of things just kind of tugging our attention, our direction in different ways, Lord, we just pray for your clarity just to shine through that, Lord. Just to help us to focus our eyes on you and the things that you want us to see, Lord, the things that you would like us to spend our attention on. Lord, we just pray just to calm our hearts and calm our spirits, and just to understand that as you promised, you would take care of us, Lord. We just put our faith in you. Lord, we just pray for that faith also. And we just pray just to influence those around us, that we can point them back to you, Lord, in whatever way that might be. We just pray that you give us the opportunity to share you with somebody today also, Lord. And we just pray this in your name. Amen. All right. So, we finally get back to something we learned in Gen Chem 1. Right? So, if you remember, in Gen Chem 1, we learned the solubility rules. Right? And we talked about, things with group 1A metals, the sodiums and potassiums and lithiums and all that kind of stuff are always soluble. Things with nitrates and ammoniums are always soluble, that kind of stuff. And we had a chart and all this kind of stuff, and we talked about the precipitation reactions or the double displacement reactions there, and we talked about how can we predict if something is going to precipitate based off of the solubility rules. Now, when we say something is always soluble, of course, we understand that's within a practical limit, right? There's always a limit to how much you can cram into some water, right? So even if you think of something like sugar, it's not infinitely soluble, and eventually it will reach a saturation point, right? Now, we talked about saturation and solubility a little bit when we're talking about the intermolecular forces, right? When we talk about why are things soluble, or how can we predict solubility of compounds in different solvents, right? It's based off of the intermolecular forces, right? And so now we kind of expand upon that idea and say, well, exactly how soluble is something, right? So if you go, you go to Wikipedia or whatever and type in your favorite ionic compound, right? What?
Magnesium nitrate.
There you go, right? It'll list a solubility rule for you, right? Not a solubility rule, excuse me. It'll list the solubility for it. It'll say you can dissolve this many grams per liter of magnesium nitrate into water, right? And then you can go on with your life having that fact and impressing the people around you with it, right? Okay, never mind. Right? But the point being, how do we know that, right? How can we calculate that? What does it mean for us? What can we do with it? How can we relate that idea back to the principle of solubility and precipitation and how much we can actually dissolve into water, right? And we can also talk about certain things like, exceptions to those solubility rules, right? One of the solubility rules said that ionic compounds with sodium are going to be soluble, right? But if you go take a look at something like sodium phosphate, it's not really all that soluble in water. It'll dissolve, but not maybe as much as you might expect given what it is. So we can actually start to put some numbers behind this. And so that's kind of what this section of the chapter is all about, right? So when you're asked a question about how soluble something is, right, this is what we're going to answer with this section here, right? So if you see a question like, what is the molar solubility of, right, this is what we need to think about, using K to figure out how soluble something is, okay? So it's just an equilibrium expression. Because if you think about it.
You said we were getting away from equilibrium.
After this chapter, yeah. So if you think about it, right, so imagine you've got a beaker of water and you're adding whatever to it, right? Eventually you'll make a saturated solution, okay? Where you can't dissolve any more of your solid into the liquid. But there is, right, some of your stuff dissolved in the water, right? So what you're doing is you're establishing equilibrium, right? Some of your stuff dissolves, goes into the water, and some of the stuff precipitates back out, right? There's a constant change between the solid state and the aqueous state. Got it? And if we could measure the rate of that, right, the rate of things dissolving, the rate of things precipitating, then we can measure the equilibrium for that, right? Because remember how rate and equilibrium are related to each other, okay? Yeah.
Is it why if we heat a solution up, we can make it supersaturated?
What do you mean?
Like that was something that was discussed earlier in the semester, is that if you've got a bunch of a compound in an aqueous solution, and you heat the solution up, then it can be, then the, like, the amount of stuff that the solution can hold.
Solids get more soluble at higher temperature, right?
Yeah.
Yeah.
And
So
then
why
if you
is
cool it
that?
down, it's super solid, it's like super saturated.
Well, it can become that, right? Sometimes most of the time it'll just precipitate out, right?
Okay.
Yeah. But the question is, why would, it's a good point to think about, why would increasing temperature increase the solubility? Well, we're establishing equilibrium. What changes in equilibrium constant?
Heat.
Temperature, right? So that's why whenever you see these types of problems also, it's always saying, what is the solubility at this temperature, right? What is the solubility at this temperature? All these kind of things. In fact, pretty much every problem that you guys have seen with equilibrium has some kind of temperature stated with it, right? Because that's the important part with it, okay? Anyway, so that's what we're gonna get to with this. So, we are using another form of K. Does anything change in terms of what we've already learned with K?
Probably not.
Nope, right? K is K, all right? KEQ or KAs or KVs or KWs or, I don't know if we talk, I can't remember now if we talk about it, but there's KFs, oh yeah, we will actually, yeah. KFs, which are formation equilibrium constants, like all this kind of stuff. It's just based off of products and reactants, that's all it is. The concentrations of those, okay? The concentrations or the pressures if we're dealing with gases, okay? So if I ask the question, what is the K for this, let's say, expression here, right? Where we have some silver chloride and we're dissolving it into water, right? So we're just breaking up an ionic compound into its constituents, right? Okay, well, products over reactants, right? I don't think I'm going to really spend too much time on this because I imagine that you guys are well aware of what's going on here at this point. Right? So we would come up with an expression like this, right? That's it. Now, since we're dealing with solubility, what we'll have here is the KSP, right? So whenever you guys see KSP, we're talking about the solubility product.
Why aren't we writing AgCl underneath? Is that just because they're spectators?
Solid, right? The concentration of solids are not going to change, right? Good? So think about this for just a second. Where does this is important, I promise I'll get back. Where does this come from? Not like, where on the planet do we mine silver? Where does that specific silver ion come from? It comes from what? What you're adding into it, right? What you're trying to dissolve. Okay. You guys with me on this one?
No?
Okay, half of you guys are, right? You guys get what I mean? Like when I take some silver chloride, I measure it out on the balances that we have upstairs, and then we go to the balance that works, right? And then we measure it out again. Right? And then I take that and I try and dissolve it into water, right? The silver that's in solution, the stuff that's dissolved, comes from the silver chloride that you added into your beaker of water. You guys with me on this?
Yes.
Right? What's important to think about here, right, and this relates back to one of the previous concepts that we thought about, is how do how do ionic compounds break apart? Okay? Right? So the equivalence that we have, right? For every one silver chloride, we make one silver and one chloride. Okay? But if we change the charges, right? If we have two chlorides or two silvers, right? Then we're going to change the relative concentration of the different ions in solution. This is one of the tricky parts that comes out of this part of the chapter here. Just making sure that we can break things apart when you put it into solution. Got it? So make sure you guys are breaking apart ionic compounds when you're trying to dissolve them. Okay? But all the silver here has to come from the silver that you guys put into solution there. And that's going to help us answer the question of how soluble something is. Okay? Yeah.
So for this K, you're not going to divide it by the reactant?
No, right? Because the reactants are solids, right? Remember,
Oh,
pure
okay,
solids
yeah.
and pure liquids are not part of our expression.
Okay,
Okay?
thank you.
Yep. Oops. And so we could just carry this on here, right? Kind of follow the same principles and ideas. Right? I could ask you guys to write KSPs for this. I'm not going to, just because I assume that at this point it'd be a little bit of an excess to kind of stop and talk about this too much, right? But the point that I was trying to make is think about where the 3s and the 2s and all that stuff comes from, right? So far, when we're dealing with the acids and the bases and the Kas and the Kvs, everything's usually in a 1-to-1 ratio, right? So we might have gotten out of the habits of thinking about what our stoichiometric coefficients are. Right? But always make sure you have a balanced equation is all I'm really saying with this, okay? Because if you don't have your exponents up here, then you're going to get the wrong value, right, for K, and then your calculation is going to be off for this stuff, okay? What's up?
I thought those exponents came from the coefficients,
They do.
not from the.
But in this case, the subscripts of the ionic compound is the coefficient of the ionic individual components.
So what we're saying here is,
Oh, I see what you're saying.
yeah, so if we take silver sulfate here and we break it apart, right, you're going to make 2 Ag1 pluses, right, plus 1 SO4 2 minus. Right, that's what I'm trying to say with this, right? How many equivalents, how many silvers are part of that ionic compound there, right? That's one of the tricky things to, well, not tricky, but it's one of the important things to remember, right? Guys with me on that?
Yep.
So what's going to be really important when you're working through these types of problems? Well, we're going to have to know these things called our polyatomic ions, okay? Now, we've never seen these before, right? No. Right? But knowing the names, knowing the charges, all this kind of stuff, right? Because we're going to have to balance charges and all these kind of things with it, okay? So as I promised, I think last class or maybe the one before, these polyatomics are going to show up over and over and over and over and over again. You got to know it, okay? And I think I made this promise to you guys at the beginning of the semester. I can't remember, but I'll make it again here. I'm never going to ask you guys to memorize or know something that isn't useful somewhere else, okay? My interest is not in that you guys have what I refer to as bar trivia, right? And what I mean is so you can go win your bar tab at the trivia night, okay? Right? Oh man, I memorized so much of Wikipedia. That's not my intent. My intent is for you guys to understand stuff. And knowing your polyatomic ions is essential to understanding a lot of chemistry as well, okay? So then here's...
That's something really sad, though.
Nope. But hang on to your thought. I'll be happy to hear it later on, okay? Okay, so typical question. calculate the solubility in moles per liter, right, of silver chloride, okay? Another way that this question might be asked is, what is the molar solubility of silver chloride, right? So whenever you see molar solubility or solubility, they're kind of just referring to the same thing. AKA, how much silver chloride can I put into solution? That's all it's saying, okay?
Wait, quick question.
Yep,
KSP, so
yes.
S stands for solubility?
Yeah, solubility product is basically what SP stands for, okay? All right. So, much like with the KAs and all those other kind of KBs, blah, 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 yada, 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 right? Appendix D in your textbook, right, has a giant listing of the, I believe it's Appendix D, I'll have to, you guys can verify here if you have it, right? It has just a list of what the common KSPs are, okay? So when you guys are going through and working these problems or whatever it is, it's in your textbook, or I'm sure you guys know what this thing called Google is, that'll tell you also, right? The point being, KSPs are something that's tabulated. So you can just look it up, it's what it is, okay? All right. So how does this, or how do we start to set this up? All right, well, first things first, write your expression. Okay. If we want to think about this and expand it a bit, right, the reaction that's going on is, right, what we talked about there earlier, this. Right. So when I take some amount of silver chloride, okay, I make X silver and X chloride, is what it is, right? Some concentration of silver and some concentration of chloride that comes from, right, the amount of silver chloride that I added into there, okay? I'm really trying to draw you guys' attention to where does the silver and chloride come from, because if I know my value of silver, right, then I know how much of this I can put into solution, okay? The relationship between the ions and the solid that goes into solution there is what I'm asking you guys to figure out, okay? It'll become a little bit more obvious when we do one of these other problems that's coming up, okay? But everybody following with me on this, right? Remember, we're at equilibrium, so some of the silver goes into solution, then some goes out. We can only reach a maximum concentration of silver chloride at equilibrium. Is everybody with me on this? This is where equilibrium becomes tricky, right? I can only put so much in the solution before it precipitates out. You guys with me on that? Okay.
It's like, it's too heavy for the water and eventually the water gets overloaded and drops it.
Well, yeah, kind of. It's not really weight-based, but I mean, if you want to think about it that way, that's fine, right? So what does this mean? That means that 1.8 times 10 to the negative 10 is equal to, right, x squared, right? You guys with me on that? Yeah.
How come it's just equal? Like, how come?
KSP,
Yeah.
right, is equal to x times x, right? X times x, so.
How do we know that AG and CL will? Oh, okay.
Yeah. Yeah, it's the same K as everything, right? We're just now bringing it into a new idea of solubility rather than acids and bases and that kind of stuff.
Because you can't have a CL that is in solution without an AG because they're together.
Correct. Yeah. Well, hang on to that thought,
Okay.
right? So we'll see. We'll make it a little bit more.
Oh, I
Yeah. We'll make it worse. Don't worry. Right? Not really, but we'll follow along with that line of thought. It's a good question. Good. So we take the square root, and we get something like what?
1.34 times 10 to the negative fifth.
Sounds good. So 1.3 times 10 to the negative fifth equals x, right? Which is our molar solubility of silver chloride. I can put 1.3 times 10 to the negative 5 moles of silver chloride into a liter. Now, some of the questions in the book are going to ask you how many grams can you dissolve into a liter. Got it? So remember, what is x? We're solving for concentration, right? Moles per liter. So I can convert moles into grams, and then if you're given a volume, you can convert grams per liter into grams, okay? So just paying attention to the units that are part of this. Now, X in this case also tells us exactly what the concentration of the silver and the chloride are also. You guys with me on this? This happens when everything's in a 1-to-1-to-1 ratio, okay? So pay close attention to what does your X represent, okay? That's not too bad, right? Nice, easy. Why can't life just stay like that? Well, life's a little bit more complex. Okay, so if we take this same idea then, right, we're just silver chloride, okay? And then we kind of bring in Le Chatelier's principle, okay? So adding more silver chloride will shift the equilibrium, or we should say the reaction, or whatever you want to think of, to the left, okay? If I have more stuff on this side, right, I'm going to shift back over to that side there. You guys with me on this? That's just what Le Chatelier's principle says, right? If I add more stuff to one side, it's going to shift in the opposite direction. If I take more stuff out from one side, it's going to shift to that, okay? And so what they call this is just a common ion effect. If I already have some of my ions in solution, okay? So now let's think about it this way. So now we're back in the lab. I've got a beaker of water, okay? And I dissolve some sodium chloride into that water first. Okay, so now I've got sodium and now I've got chloride in that water. And then I try to dissolve silver chloride. It's going to change how soluble that becomes because I already have chloride in solution. Okay? And I can only put so much chloride into solution before the silver chloride precipitates back out. You guys with me on this one? I'll show you guys mathematically what we're just walking through there. Yeah, what's up?
What if you tried to dissolve magnesium sulfate in a sodium chloride solution? Since there's no common ion, would the dissolution proceed?
Yeah, we'll do an example like that in a little bit, right? So we're talking about a common ion, meaning there has to be either silver or chloride already in solution, right? If we have a completely different thing in solution, then we have to think about, will a precipitation reaction occur? And, how much, or, that kind of stuff that goes with it. So, same idea, but a different approach to it, so to speak, okay?
Would magnesium chloride be precipitate? Would magnesium chloride be a precipitate, like would that precipitate?
In what reaction?
If you mixed a solution of sodium chloride with magnesium sulfate?
Magnesium sulfate would precipitate out of it first, right? Before magnesium chloride would. Yeah, like I said, chlorides are very, very soluble, right? It's the sulfates not so much. What's up?
So when you have a reaction with common ion, how do you know which one is gonna precipitate out? So is it gonna be the
We're
less-
talking about this reaction here, right?
Yeah. No, I'm talking about the common ion when you have silver chloride and sodium chloride.
Yeah.
So how do you tell which one's gonna come out? Is that gonna be less soluble?
The solid is what we're talking about, right? Not the chloride. You can't just precipitate out an ion.
Right.
Yeah. I'm sorry, I don't understand what I don't.
Never mind.
Oh, are you saying how do we know that silver chloride and not sodium chloride precipitates?
Yeah.
Oh, okay, I got you. Right, so there's an issue of where you look at the KSPs of things. Right, so much like when we looked at like KAs or pKas, right, that gave us information about strong versus weak acids. Right, if you look up the KSPs for sodium chloride versus silver chloride, there's going to be a huge difference in between, right? And the one that's less soluble, the one that has a lower KSP is going to precipitate out first,
Okay.
right? Good question. All right, so let's take a look at this example here. So when I learned how to do solubility stuff, okay, our professor told us to use S's instead of X's. Why? There's no real reason to it, aside from the fact that now we're dealing with solubilities. So it's just easier in my mind, and so oftentimes I kind of forget and switch in between the X's and the S's just because of my experience, I guess, so to speak, right? But either way you guys want to do it is just fine, right? So if you guys see S's on my notes, we're just doing KSPs, right? We're talking about the solubility stuff for that, okay? So calculate the solubility of lead iodide in water, and then if we have a 0.01 molar sodium iodide solution, okay? So we'll do part A here first. We write up our solubility expression, right? And we have to pay very close attention to how much iodide and how much lead comes from each lead iodide here, right? So that's where the S and the 2S come from there, right? X and the 2X, either way is fine. So see what you guys can get here for these problems.
I left my calculator to Katie, so I can't give a number.
Ah, I see. Already, it's early in the morning, be blaming somebody else.
I'm gonna run back to my room and get my spare calculator.
Wait, are you serious?
Yeah, I like having a calculator.
Rachel, come back here and sit down.
Whatever she misses, you can watch on.
I guess, a little bit excessive there. All right. Life's an adventure.
She's running.
Life is always an adventure with
Should we lock the doors on this?
She'll come through the window.
You think she'll come through the window? Yes. All right, so we've got this. My goodness, my brain is. Okay, let's try this writing where it is actually legible. Okay, lead 2 plus, 2I minus, right? Which means we have S, right? And 2S squared. Good?
Why do we keep the coefficient with I?
I'm just saying what the concentration for I is here, right? We've got, there's twice as much I as there is lead. 2 I's come from each one lead iodide, right?
What is
Just, it's a variable, right? You could just call it X, right? So just like we did X in the previous one, sometimes you'll see me use S just because we're dealing with solubility of stuff. It doesn't really matter. Either way, whatever you guys want to do with it. What's up?
So in the case that you're basing everything off lead,
Yes.
you need to.
Well, not lead iodide,
Lead
right?
iodide.
Yeah.
Then you need to have 2S in the concentration. Okay.
Yeah. Good? So if we do this here, right, 4S squared times S, so 4S cubed.
Why do we also square it?
Well, our coefficient is 2, right? Remember when you express K, our coefficient is our exponent there, right? So remember, what I'm trying to calculate, right, this is concentration, right? Right? Concentration means how much of my stuff do I have dissolved in solution. I've got twice as much of my I as my lead, so I have to multiply that by 2 there. You guys could say this is X and then this would be 1/2 of X, right? Either way is fine, right? We're just saying how much of our stuff comes from the lead iodide. So 8.7 times 10 to the -9, 4S cubed, right? So now's the time where we start to learn where our cubed roots are and stuff like that in our calculator. However, let's assume we don't have a cubed root function in our calculator. How do you take care of that? Right, so if you raise something to the 1/3 power, that's the same thing as taking the cubed root, right? Or over to the 1/4, that's the 4th root, 1/5 is the 5th root, yada, yada, yada. What's up?
Why is it 4S? I would expect it to be 2S.
2 squared, 4S squared, right? And then S times, or S squared times S, you add your exponents when you multiply together, right? Yeah, don't forget you add exponents when you multiply, right? Good?
So the exponent's gonna apply to everything?
No, just to this. Everything in here, yes, yeah. Yeah. Because you basically, remember this basically says 2S times 2S, right?
And so we don't really care about the reactants
They're just,
These are solids, right? So they're
Yeah.
not part of our K
oh,
expression.
it's solid.
Yes.
Okay.
Sorry, I should be careful and put that stuff in everywhere, but remember our stuff over here is. Get that, right? Yep. Good? Okay, so if I plugged everything in right, then I got S is equal to, let's see, 1.3 times 10 to the minus 3, right? So what does this tell us, right? S tells us a couple of things here, right? Remember the first thing it says is calculate the solubility of lead iodide in water, right? That's where our S comes from, or that's why we're thinking about where do our ions come from, right? There's a maximum amount of the stuff we can have in solution, that's our equilibrium concentrations, right? Our equilibrium concentrations we can relate back to how much of our solid we can dissolve, right? That's the idea here, okay? You got it? You didn't even find it. Of course, the old snake in the boot, all right. So we got our expression of our solubility there at equilibrium, okay? So now think about this. This is something I've been leaving it off, but it's important to me not forget these things. And if it's important for me not to forget, then it's super duper important for you guys not to forget, right? What are the units here, right? This is moles per liter, right? This is a molar, right? This is a molar concentration, okay? So be careful about when the question asks you the solubility in grams per liter, or how many grams, yada, 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 that kind of stuff, okay? What's up?
Okay, I know I missed this.
Yeah?
But why is it 2 both an exponent and inside the thing? The 2 on the I, it both turn into an exponent?
So remember when you're writing your K expression,
Uh-huh.
right? When you're writing your K, we're dealing with concentrations, and your coefficients, right, is what becomes your exponents.
Right.
Right.
So why did it become both an exponent and stay a coefficient?
What's the solubility? If I ignore the whole thing about K, right? How could we calculate the solubility of, or excuse me, ignore K and then ask a question about K, right? Right? What would the concentration of I be? It's twice that of whatever the lead is, right? So we have to express what the concentration of iodide is,
Okay.
right? And that's going to be twice whatever this is here.
Okay, I got
Right?
you.
And then it's our exponent, so it becomes the square part, right? But the reason why, or maybe I should draw this back here again, just to, I don't feel like doing my important dance today. I'm a little bit tired, right? But right, this is one of the parts that gets missed when you guys are working through these types of problems, right? You forget to bring your exponents out because it's already written here, all this kind of stuff. Go through and double check, okay? Go through and double check that you have everything written out first, okay? That's why when I work through these problems, I always have to go back and check myself on this, okay? Okay, good. We've answered part A, now part B. All right, so now we have a certain amount of sodium iodide in our solution. Right, so we have our beaker, we added in some sodium iodide, and now we're trying to dissolve more of our lead iodide into that. Okay? Okay, there's our reaction. Do these things called ice tables. Okay. Solids are not part of our equilibrium expression. So now we got to think, okay, what's this problem telling us? We have a beaker and we dissolve sodium iodide in, and then we're going to add the lead iodide to it. Got it? So how do we start to fill in the stuff here? What do we have initially? Well, initially, we've got a 0.01 molar solution of sodium iodide, right? You guys with me on this? Do we have any lead to begin with? No. Okay. So at the beginning, that's what we had. Now what do? For the change is when we add in our lead iodide, and we start to mix the stuff up. Got it? So what is our expression here at change? Our S or our X, right? You know, either one you guys want to use. We'll just change it up here, right, for argument's sake, right? We have some amount of lead and some amount of iodide that comes from the lead iodide, right? So plus X and plus 2X. And so at the end, X and 0.01 plus 2X are our equilibrium concentrations. Yeah?
What does S represent?
Just the same thing as X, right? Just some variable of what change is going on there, right? That's all it is.
Okay.
It's just S is used for because it's solubility, that's all.
Okay.
Like I said, either way, feel free to come back and swap those out for S's. It's not going to affect anything.
Okay.
Okay. So now we take a minute and we remember our expression for KSP. KSP is equal to lead, right? 2 plus. Bear with me for just a second, right? Okay. You guys with me on this? This is what our expression for KSP is. The concentration of lead times the concentration of iodide squared, right? Everybody with me on that one? So what do we have here? This is our expression for the solubility of iodide, right? This is our expression for the concentration of X, okay? So now let's plug in. So we have X times 0.01 plus 2X squared, okay?
Good question.
Yeah?
So, is the reason we didn't put 2 in the I here because, okay, so if you're writing this in terms of X, the equilibrium expression in terms of the X's, you would
Which
have.
we did.
Yeah.
Yeah.
Then it would be the,
Well, remember, here's where we took care of that 2 there, right?
yeah.
How much of our iodide comes from the lead. Because remember, this is the tricky part. At the end of the day, we just care about the concentration of this. We don't do anything special to it, right? We just need to figure out what the concentration of that is. That's all. Do you guys see where this becomes crappy?
Yeah.
But there's good news. And guess what that good news is?
Shortcut.
Very quickly with the, right? So remember, but this is important, right? We're dealing with K's. So if it applies to acids, right, where we can use the shortcuts, it can apply to any K. You guys with me on that? Because what's the difference between Ka and KSP and KB and KW? What's the difference between those? Nothing really, right? They're just K's for specific purposes. K is K is K, right? So we can do the shortcut here. So what are we saying? We've got a, did I write it down for you guys before? I think I did, right? Oh yeah, right? So, a KSP of times 10 to the negative 9. Right, and we're starting out with a concentration of 0.01. What's the difference in between there?
Big.
Right, a difference of 7 orders of magnitude. So can we do our shortcut? You bet, okay, you bet. So essentially what we're saying is X is much less than 0.01, our starting concentration, right? To the point that 0.01 plus 2X is really going to be equal to what? 0.01, right? You guys with me on that one? So this can simplify then to X times 0.01 squared is equal to 8.7 times 10 to the negative 9. Okay? Much easier now, right? But paying attention to when and how we can do the shortcut It's always important. Don't just assume we can do it. So if I did everything, I got x is equal to 8.7 times 10, so minus 5. Good?
Number.
Huh?
It's a bigger number.
Yeah, well, you're gonna end up dividing by this, right, to solve for x.
No, but I mean, I understand like how mathematically it's a bigger number.
Oh,
But I'm trying to think more in terms of like what that means. It means that
well, it's a smaller number than if you're comparing it to the previous, right? So let's back up here for just a second. It's a good question, right? So let me circle these two values here, right? So those two values represent our answers for A and B,
Yep.
right? The solubility in pure water up there in red, and the solubility in sodium iodide down here. So what does K tell us? Well, we got a bigger number up there versus a smaller number down here. So lead iodide is more soluble in pure water than it is in sodium iodide water, right? Does that make sense?
Yep.
Well, it should, right? Because we start out with something already part of our equilibrium expression. You guys with me on this? Remember, we already have some of this in solution, and we can only reach a maximum before the lead iodide starts to precipitate out. That's what this is telling us. Okay? So we should expect, with these common ions, that our solubility is going to be less than that in pure water. Okay?
So the second part, we're trying to see how soluble it is in the sodium iodide.
Mm-hmm.
Okay.
Yeah, when we have a common ion in there, yeah. Cool. All right. So the next couple of slides, we just have a couple of, let's say, stuff that we might come back to later in the semester. So we mentioned this briefly at the beginning of chapter 16, where most of the time we've been dealing with, sorry, I feel like I'm about to sneeze here, where we've been dealing with Bronsted acids and bases, right? The acids that produce hydronium or produce hydroxide when they're put into solution, right? But Lewis acids and bases, we mentioned them just a little bit, right? But we will see those a little bit more towards the end of the semester if we have time to talk about some inorganic complexes and things like that. So, but anyway, so what the point here is metal ions, so your transition metals, if you want to just think about them like that, right? They can act as Lewis acids, and anything that's a Lewis base, we can basically come together and start to form complexes with that, right? But we can start to use this idea of KSPs to calculate things called formation equilibriums, right? So can we actually make these complex ions is all we're really saying, okay? So how does something like that work, okay? Well, if we take the individual reactions here, right, the silver bromide dissociating into the silver and the bromide, right? That's silver plus the thiosulfate. I think that's what it is. Yeah, thiosulfate can make our silver thiosulfate complex there. Okay. We can add our two reactions together, right? We have things that are on the same side in both cases, right? So we can eliminate those and come up with an expression for the overall net reaction. Nothing really unusual there about that, right? This is stuff that we talked about when we were going through Hess's law and all this kind of stuff too, right? We can add complex reactions together to form the net reaction here, okay? So our K net is equal to KSP times KF, right? We can just merge our K values together here, right? There's our KSP, right? Here's our KF, which is just our K for this expression here, right? And we can come up with our overall K for that one there. Who cares, right? So what's the point of this here? Well, all we're saying at this point is that we can use these individual components that we've been talking about, right, to make an expression for a more complex set of reactions. That's all it is. So if you take an expression of K for the individual parts, we can put those together to form a formation K for the overall reaction that we're trying to do. That's all it is. Okay? And if you know the values for KSP and KF, then we can actually sit there and calculate what the K net is, right? You're gonna miss it, or you're gonna go back and get your calculator, is that what it is? Right? You guys with me on this one
Is
here?
that your phone?
No.
That's mine.
Yeah, what's up?
Random, not really related to this topic, but why does, in the silver and Q sulfate, why
Yeah.
does that end with 3 minus charge?
Because we are putting 2 of those thiosulfates with 1 silver ion there, right? So each of them brings in a 2 minus charge, and the silver has a 1 plus charge, right? So, good question. Now the question might be, why can we fit all those around there, right? We thought that everything should balance out, right? Which is a good question too. Okay. So anyway, when the book talks about KFs and that kind of stuff, that's all it means in there. To be frank, like, I'm not too interested in that stuff with you guys yet, okay? I'd focus more on the KSP stuff is all it is if you guys catch my subtle drift. Okay. So, now we take this idea to its natural progression. So now that we can calculate if something is soluble and how much of it is soluble, the question that becomes, will it precipitate, right? So now we can kind of relate this back to what we talked about in Gen Chem there when we were saying, hey, will this stuff dissolve? Will a precipitation reaction occur? That kind of stuff. To do that, we're going to need to look at Q and KSP, okay? So remember, what does Q tell us? Q tells us where we are along our K graph, right? It's a way to compare our values of our concentrations to our equilibrium expression K, right? And if K is bigger than it, right, or less than K, then we're going to have to reassess and get back to our equilibrium concentrations, okay? That's all that Q is. So if Q is bigger than my KSP, then I need to drop, right? I need to remove ions to get back to K. Got it? I have too much of my stuff dissolved. Remember, Q is just what? Products over reactants. And if I have a big Q, that means I have what? Too much product, so what do I need to do? Precipitate some of it out, so I get back to my value of K. You guys with me on this one? This is important. Understanding of what Q is going to tell us with relationship to K.
Big Q means precipitate, Q, fine. Small q means
So, yeah, well, yeah.
small q.
Right, so Q is equal to K, we're at equilibrium. If Q is less than K, we don't have enough stuff dissolved. Our concentrations are too low, so we dissolve more, more can go into solution, right?
If the Q is greater than K, the solid will precipitate out.
Correct, right, because remember our expression for Q is concentration of our ions, right? So the only way we can decrease the concentration of ions is to have some of them come out of solution, to precipitate back into the solid, right? Good? All right, see what you guys come up with. think about what we need to calculate here. Okay? Think about what we need to calculate here. I need to figure out if silver chloride precipitates, right? And essentially what I need to do is calculate my Q, right, for this equilibrium here, right? If I need to figure out if silver chloride is precipitating, I need to figure out Q for this. Now, what do I need to know? I need to know my concentration, right? I need to know my concentration of silver, right? And my concentration of chloride, right? In this mixture. You guys with me so far?
Mm-hmm.
So I need to calculate concentration of silver and concentration of chloride.
Mm-hmm.
But what am I doing in this reaction here? I'm taking 25 mils of one thing and 10 mils of another, and then I'm mixing it together. What's the units for concentration? Moles per what? Liter of solution, right? So much like with the buffers, we have to pay attention to how much stuff is mixed together, okay? And remember, just like with the buffers, we take everything out of concentrations first, deal with the moles, and then come back and turn it into concentrations. Okay? So step one, get rid of your concentrations for the moment, right? Or really, I should say, figure out how much of your silver you have, right? Figure out your concentrations there after you mix the stuff together. Either way, you guys want to address that. So see what you guys come up with. Units of volume, right? Liters. We'll give you units of concentration. So every given molarity of volume. And you can get moles out of that, right? So you get how many moles you started out with, and then you divide it by the total moles at the end, or the volume at the end, right? So tell me how many moles of silver ion you have, how many moles of chloride you have. And then tell me the concentration after you mix the two. You multiply the two, right? To get the moles.
Yeah, but the most chloride just comes from this,
Mm-hmm.
not this one.
Well, there is no chloride.
Yeah.
Yeah.
Yeah, it is.
Okay, yeah. short on time here. So let's just see how far we can get. Alright, so if I let's figure out moles of chloride, so 0.0025 moles, right, per liter. Right, just bring that from here. There's our chloride source, right, times our 0.025 liters. How much of that we have? 6.25 times 10, negative 5 moles of chloride. Sounds good. That's where I'll get my info from moles of silver. So 0.01 moles per liter times 0.01, right? Liters. 1 times 10 to the minus 4. You guys with me on that? So I'm just saying, how many moles do I have in my starting solutions? Then I mix these two together, I'm going to have a concentration as soon as I mix them together. All right, so we basically want the snapshot as soon as we mix them together. You guys with me on this one? So we're not calculating K, we're really calculating Q. Right, we have these two beakers, we say, go, and then we mix them, right? And that's the moment where we're calculating how much silver and chloride we have. Got it? Cool. So I think we're out of time here, so we'll pick this up on Friday, right? But you guys can finish this up on your own also, right, before we get there, right? So calculate Q and then compare it to the KSP and answer the question, will something precipitate, right? And take a look at the previous slide there where the answer is yes or no, right? How'd you get this? Because this, no, how'd you get that expression? This is our expression for Q, right? Concentration.
Because we're not doing, wait.
This isn't common iron, right?
Why isn't HCl going?
That's our